Hello everyone and welcome back to yet another lecture of MRI Physics Explained, perhaps the most important lecture. Today we are going to tackle T1 contrast, which you have probably heard, or if you're a radiologist, have said in your reports hundreds if not thousands of times before, but which truly explaining and understanding is in the upper pantheon of MRI physics subject difficulty, right alongside phase encoding and K-space. And as always, we'll try to explain it in as simple and straightforward way as possible. And if you like these lectures, please subscribe, like, and comment to support what we do here, follow us on social media, or consider donating using the links below. And with that, let's get to it. On the previous lecture on T2 contrast, we left on a cliffhanger. We described how our time of echo, TE, the point at which we decide to compare all the T2 decay curves coming from each voxel, sets how heavily T2 weighted our image will be. And we hinted that we needed to minimize T2 contrast in a T1 weighted picture shown on the right. We did this by choosing a short time of echo, the point at which the individual T2 decay curves have yet to significantly deviate and will therefore not contribute large differences between our measurements. So how does T1 play into this picture? Pun intended. Let's start by going back to where it all began when we first discussed T1 recovery in our very first lecture. We showed that if we could look at the water protons in a cube of matter within the body, they normally are aligned randomly. But if we put the object in a very strong magnetic field, the protons will align parallel to the magnetic field, either with the direction of the field or against. However, because it's more energetically favorable to align with the field, slightly more protons align with than against. We're talking a few out of a million, and this creates a net magnetization along the direction of the magnetic field. We literally are building a magnet within the body. But this doesn't happen instantaneously. Like most good things in life, it takes time. As shown in this familiar figure most of you have all seen before, when we place someone inside the scanner, it takes time for this net magnetization to reach its maximum value, growing with a time constant we call T1. This process is better animated here. Let's see that one more time. Note how the more protons align with the magnetic field than against, the more this net magnetization grows, reaching its maximum value when all are aligned. So this brings us to one of the most famous, if not the most famous MRI physics animation of all time. You will always be shown some version of this in any MRI physics course, and will show it in steps, mainly because of my limited animation skills. This graphic intends to show you that, from our resting state with our net magnetization aligned with the B0 or z-axis, same thing, after we knock this into the XY plane with our RF pulse, it starts dephasing as time goes on, which is true. This is the decay of our T2 decay curves. We then induce another pulse to flip these protons 180 degrees, shown here, at which it begins to rephase, perfectly realigning back along B0. My question to you is, from all we've learned so far, does this make sense in terms of current being induced in a coil? Let's place our receiver coil parallel to the B0 z-axis and try to visualize the current being generated in it, knowing the closer these arrows are together, or the more in phase they are, and the more perpendicular they are oriented to the coil, the more current will produce. Having trouble? So did I. There's something off here, right? I stared at this for days, maybe weeks. and could not get physically what's going on here in the most famous of MRI animations. Why would these rephase at a maximum parallel to the z-axis, where our coils see no signal at all? Remember way back to Lecture 1, where we discussed that through Faraday's law, we only induce current in our receiver coils when this net magnetization is perpendicular to them, whether that be perfectly in the xy plane as shown, or at some oblique angle where we still have an xy component. But when this is perfectly aligned with the B0 z-axis, we see no current. So how does this make sense at all? Let's look at a similar animation portraying this concept, this one from the PIRL YouTube channel. We're not trying to pick on them, in fact quite the opposite. Their animations are much better than mine. But again, we seem to be showing something that doesn't quite make sense in our current framework of understanding. Here we see our net magnetization, the arrow in purple, spinning after being excited, and alongside it we are being shown its subcomponents in both the xy plane and z-axes. Notice how the purple arrow spirals upward, building its full size right as it perfectly realigns back with the z-axis. And it's tracing out a spiral in the xy plane, representing our T2 decay, shown below. Does anything strike you as odd or puzzling here? It might help if we break this down in a stepwise fashion. So we have our net magnetization, the red arrow, fully developed along the z-axis. This is as if we took our patient, placed them in the scanner, and waited some time. We displace this with our RF pulse, let's say 90 degrees as shown. Remember, we can choose how far we want to knock this into the xy plane, but for simplicity, we'll keep it at 90 degrees for these examples. So according to the prior animation, this will now spiral up, getting smaller and smaller until it fully aligns with the z-axis. And from what we have already learned, as this spirals around, it will induce a decaying current in our receiver coil, animated here. Let's take a look at that one more time. We apply our RF pulse, knocking the net magnetization into the xy plane, and upward it spirals, inducing current. Now here's my question for you. Do you really think, as these animations are portraying, that these two processes, the T2 decay of our signal and the rebuilding of the net magnetization along the z-axis, happen at the same time? Take a look at this again. Do you really think this rephases and reaches our original starting net magnetization value perfectly at the same time? Or this purple arrow spirals, producing our signal, again perfectly ending at the same time we fully recovered our original net magnetization along the z-axis, ready for the next pulse. Doesn't this seem a bit too coincidental? So we've honed into something that smells afoul in the physics world, right? We can't make physical sense of what these animations are showing. And we have this seemingly too perfect timing of two different processes. So we are going to make a small but hugely important change to these animations. We are going to disconnect these two processes as shown. We are still going to precess around the z-axis after excitation, but we will not magically return to our starting place at the end of precession. So going through the steps again, we apply our RF pulse to our starting net magnetization. We knock it into the xy plane, 90 degrees in this example. and it will quickly precess about the z-axis, generating signal in our coils. And a huge point here, the signal is then lost. We are not back at our original starting point like all these animations are showing. We then have to wait. And wait. And wait. Until we have fully realigned all those protons along the z-axis and built back our maximum net magnetic vector. Let's see it again. We apply our RF pulse, knock it into the XY plane. It quickly precesses, producing signal, and then it's over. The signal is lost. And we wait, and wait, and wait for our net magnetization to build back up. So this highlights a critical point. T2 decay occurs much more quickly than T1 recovery. These processes do not happen at the same rate, contrary to what all these classic animations show. Looking at this a different way visually, the classic animations are portraying this process. After our RF pulse, we generate our signal, T2 decay, while quickly rebuilding our net magnetization, T1, both occurring at the same time. But this is not accurate. What really is happening is this. We do not fully rebuild our net magnetization by the time this T2 decay fizzles out. Not even close. It's even more exaggerated than this in real life. And critically, we cannot see this T1 process. This is happening in the background, another huge conceptual leap that current teachings fail to flush out. Remember, the only thing our MRI machine can see is T2 decay. We proved this in Lecture 1, and also hinted that this raises a perplexing question of what T1 is. We know it means something, and we have T1 weighted images, so what is it? This is the question we're now going to answer. But you will never again fall for this animation, right? You will recognize that these processes, T2 decay and T1 recovery, are separate, and that T2 decay happens much faster than T1 recovery. So then what is a T1 weighted image? Knowing that contrast has to represent differences in our measured values. Let's play a game. Hopefully you all recognize this wholesome game that's fun for the whole family, where you build a tower from wooden blocks and remove one piece at a time until it falls over. Let's use these blocks, but we're going to switch up the rules a little bit. The rules of this game is that 3 people each get a set of blocks, and the goal is to build a tower as tall as you can in 10 seconds. After 10 seconds have passed, everyone stops. We'll knock over the towers and measure the spread of the blocks, the largest spread being the winner. So let's say person number 1 builds a tower this tall after 10 seconds. Going to be honest, it's kind of weak. They spent so much time being OCD, perfectly aligning the blocks, that they forgot that the point was to build it as tall as possible. This person has a bright future in academic medicine. I laid out a tape measure for reference so we can actually measure the spread. Let's see what happens when we knock down this tower into the XY plane. Not surprising, we measure a small spread. It's hard to read, but around 10 inches. Let's see how person number 2 performed. Here's person number 2's tower. As you can see, it's slightly taller than person number 1's. Maybe a teeny bit more crooked, but not bad at all. This person could be the unsung hero of academics, keeping numbers in check while providing good patient care, out of the spotlight, but will probably take a private practice job with 26 weeks vacation. Let's see how their tower fares when we knock it over. We can see that their measured spread is larger, near 20 inches, almost double that of person number 1. They built a taller tower, and naturally, it creates a large footprint in the XY plane when knocked down. Finally, we get to person number 3, whose sole goal is to crush the tower and ram through as many blocks as possible. Bound for the private equity practices, they live for the paycheck so they can keep up with the Kardashians. They build the tallest tower as fast as possible while trying not to miss any construction flaws that will get them sued. Let's knock down their tower and see what happens. Not surprising, we get the biggest spread of them all, measuring a near whopping 25 inches. So to compare, here is person number 1's tower knocked down after 10 seconds, person number 2's, and person number 3's. We see there is a direct relationship between how fast and tall the tower is built given a set time and how big of a value we measure after knocking it down. So once again, knowing contrast represents differences in our measured values, let's take this wooden block example and apply it to MRI physics. Let's start by going through what we know. We have built our net magnetization along the z-axis and apply our RF pulse. This knocks it into the XY plane where it precesses, generating signal in our receiver coil known as T2 decay, eventually completely dephasing, at which the signal is lost. In the background, which our MRI machine can't see, we need to wait. And wait. And wait for the net magnetization to regrow back to its maximum value. If we apply our RF pulse again, we'll generate the same signal again, and our process repeats. Are we good? So here's the million-dollar question. What happens if we apply our next RF pulse earlier? If we don't wait for our net magnetization to fully regrow back to its maximum value before again knocking it down? What do you think our signal recorded will look like now? Again, our net magnetic vector precesses about the XY plane. We record a decaying signal known as T2 decay, but it's slightly different than before, right? Notice overall, the amplitude of the signal is lower, as is our spiral in the XY plane. Let's continue this and apply our RF pulse at this point, even earlier, when we've rebuilt only a small portion of our net magnetization. Like before, we still get a precessing net magnetic vector. We still record a decaying signal, yet this time, it's even smaller than before, as is the size of the spiral in the XY plane. Let's compare all of these on one slide. Here was our T2 decay curve recorded when our next RF pulse was applied very early, compared when the pulse was applied a little later, giving our net magnetization time to grow a little bit more, and when applied after waiting a long time, enough for it to build back to its maximum value. Notice that the more time we allow for our net magnetization to regrow, just like the taller we were able to build our wooden block tower, the larger the measurement or signal is generated when we knock it back down. So let's look at how long it might take for different tissues contained within voxels of our slice to regrow their maximum net magnetization after being knocked down. Let's start with this voxel containing mostly fat. It might have a T1 recovery curve that looks like this. A voxel containing soft tissue might be a little slower and take more time to rebuild its net magnetization compared to fat, as shown here. A voxel containing CSF is even slower than fat and soft tissue, spinning and spinning happily after excitation for a long time before deciding, hey, party's over, let's realign back with the z-axis, shown by this curve. Finally, let's graph a voxel containing bone. It contains few protons, producing little signal, and takes a long time to regrow its maximum value. I want to again emphasize we cannot see this process. It is happening in the background, either when we first stick someone in the magnet, or immediately after we knock everything down into the XY plane with our RF pulse. Just like how we broke down the T2 decay signal coming from the entire slice into that coming from each voxel summed together, we can do the exact same thing here, breaking down the net magnetization from the entire slice into smaller magnetizations coming from each voxel. Let's take away the arrows for now to make this look simpler. Knowing that contrast represents differences in our measured values, where on this timeline would you want to apply our next RF pulse to produce the greatest differences between our T2 decay signal? If we replace the word net magnetization with current, which we just showed there's a direct relationship between, think of the wooden blocks, where would you want to apply our next RF pulse? We would want it around this region, right? If we apply our next RF pulse here, we would produce large differences in the T2 decay curves coming from these voxels. Remember that these curves are merely portraying how big of a net magnetic vector each voxel has rebuilt at a time point after excitation. This scenario would produce T2 decay curves that look like this. As you can see, the voxel that rebuilds its net magnetization fastest in that time period will produce the most signal and vice versa. So when we select our time of echo, TE, we will get widely varying measurements. And we know that differences in measurements is what gives us our contrast. Importantly, this time until we apply our next pulse is called the time of repetition, or TR, denoted here. But more importantly, time of repetition will dictate T1 weighting, which is how much this process we call T1 recovery will produce differences in our measurement, as we just went over. So for the image shown on the right, a T1 weighted image, we will need a short time to repetition, TR, to maximize contrast from this physical property. How about this image? How long would we want to wait until we apply our next RF pulse? What kind of image am I showing? So this is a T2 weighted image in which we want our differences in measurement to mainly come from differences in T2 decay rates, not from differences in T1 recovery times. So in this case, we would want to wait a very long time before we apply our next RF pulse. We would want to wait until the magnetizations in each voxel fully achieve their maximum height or strength before knocking them into the XY plane again, so that our differences in measured values come predominantly from differences in T2 decay rates. So a long TR time will minimize T1 contrast. And correlate with this picture. Each voxel has fully rebuilt their net magnetizations along the B0 z-axis, so when excited by the next pulse, their T2 decay curves will have little variation due to T1 effects, only from the rate at which they dephase or decay. I gave each of these curves the same decay rate for visual purposes, and in this instance you can think of them all representing fat, the same tissue. But if they're different tissues, they would in fact have different decay rates. Let's wrap up this lecture with a few side notes. Because this process of T1 recovery, rebuilding our net magnetization, refers to how quickly the precessing protons can shed their energy into their surrounding environment and realign with the B0 z-axis, it is sometimes referred to as spin-lattice interactions or longitudinal recovery. These all mean the same thing, and there's no reason it needs 3 different terms, but it's board testable and you just have to memorize it. So where does this term lattice come from? A lattice, not to be confused with lettuce, which is just as disgusting as MRI physics, is a fancy term in material science to describe how the atoms are arranged in a framework fashion in a material. Think of the arrangement of carbon in a diamond. The scaffolding, so to speak, is a lattice. So a lattice is not lettuce, but lettuce does have a lattice. Quote of the century there. Also, the greater the flip angle, the more energy must be shed into the surrounding tissues to realign back with the B0 z-axis. Therefore, as we said in previous lectures, the greater the flip angle, the more tissue heating we get. And just like in T2 decay, somebody somewhere needed to get their name on a paper and they set a definition for T1 recovery. So the number that was decided upon was 63%. And this is the definition of T1 recovery, the amount of time it takes for a tissue to rebuild 63% of its maximum net magnetization. Some references will say the time at which 63% of the signal has recovered, but I think a more accurate term is the time at which 63% of the net magnetization has recovered. Signal is a little too general here and can be misleading. So if this line at 100% represents the maximum net magnetization each tissue will achieve if we wait long enough, this line at 63% would represent the tissue T1 recovery time. And you can see it's different for each tissue. But once again, this is a huge distractor. This is not what we are doing in MRI imaging. We are building a picture sometimes for the sole purpose of exploiting differences in these T1 recovery times. We are not trying to figure out some arbitrary 63% value for which our signal has recovered, so memorize this for boards and then forget about it. Remember, we're not building an image of a pure substance like this bottle of water which has no contrast. We're building a contrasted picture from many different tissues, so don't fall for this distractor. Up next, TR, TE, and image weighting. We're going to see how these parameters interplay with one another and how that ultimately selects for our traditional T1 and T2 weighted sequences, as well as others. So if you like these lectures, please subscribe, like, and keep the comments coming. I love hearing from all you learners from around the world. These were the Creative Commons images used in the lecture. A disclaimer on all the graphics and animations. And we'll see you next time for the grand finale of the basic, but not so basic, MRI Physics Explained lecture series. This is Dr. TE, signing out.